So today, this is our first online lecture for Chem 3A, and we're actually starting on Chapter 15. So when you do your homework, do the homework for Chapter 15. I'll give you instructions on how to be turning in homework this week and next week and the following weeks as long as we're online. But for now, let's go ahead and get started. I'm going to take a little bit of a turn in this lecture, and I think most of you will find it interesting, a little bit more on kinetics than I normally do for Chem 3A class. But we're talking about chemical kinetics and equilibrium. And when we say kinetics, really what we're doing is we're talking about how fast a reaction will go. So speed, like chemical kinetics, is related to the speed of a reaction. So when you think about speed, what do you think about? Yeah, well, you're probably thinking about like how fast your car goes or how fast you could run. And when we do the rate, that's called miles per hour, right, or feet per second when you're running. And chemical kinetics is typically measured in units like molarity per second or moles per second. We actually measure how fast the molecules are transforming during a chemical reaction. So for example, let's say my reaction is A goes to B. And I'm trying to do this with the front-facing camera because I think people find it a lot disconcerting just to hear a voice all the time. So A goes to B. So if we're looking at the change in A over time, that would be the rate of the reaction. So molecules of A or moles of A. Now, there's something very different that we talk about in chemistry when we're measuring quantities of material, and one of those is equilibrium. So you notice how in this chemical kinetics, what I've done is I've used an arrow that goes in one direction. But when we're talking about equilibrium, we typically use an arrow that goes in two directions. So when we talk about A goes to B, we also talk about B going back to A. And we call this idea reversibility. Like many chemical reactions are able to go both in the forward and the reverse direction. Okay, so what we're going to be doing then in kinetics is defining how fast something goes. And I'm going to give you an interesting example of how we can use chemical kinetics to analyze things perhaps you don't expect that are related. But it turns out many physical and biological processes are related by the same mathematics. And so we'll talk about that. But then we're also going to talk about equilibrium. Equilibrium, the mathematics is a lot more easy to handle. The kinetics equations can be a little complicated, and I can walk you through those if you're really interested. But in chemical equilibrium, we're just trying to see how far a reaction goes. So when the molecule A goes to B happens, at the same time, some of the molecules of B in a reversible system will convert back to A. And it turns out many chemical reactions are reversible. So we're going to get for A to B for kinetics, we're going to get a rate constant, which is usually a lowercase k. And for A goes to B in equilibrium, we're going to get an equilibrium constant. That's going to be a capital K. And there's different kinds of Ks because we measure equilibria for both reactions that have gases or reactions that are all aqueous or combinations of two. And so if we have everything in the gas phase, we'll call it Kp because we'll be measuring pressures. If we're measuring things in solution phase, we're going to have Kc, so we'll be measuring things in concentration units. And then if there's a mixture of concentrations and pressures, then there's not a clean designation. We don't say Kpc, we just say K. K covers it all. Okay, so let's talk a little bit about reactions and how fast they go. So reaction rate, how fast a reaction goes. We use something called collision theory. So in order for a reaction to take place, two molecules need to collide, either for the transfer of energy or to form chemical bonds, because we've just studied structures of molecules, and you understand how we can put the structure of the molecule together by placing electrons. But it also turns out when molecules react, they make new substances, so new bonds have to be formed and some bonds will have to be broken. So in order for two molecules to react, they have to collide, okay? Now, there's a couple of other, and I'm going to talk through a lot of this so I don't write on the screen and bump through it, but when molecules must collide to react. Now, here's the interesting thing about this. When we're in the time that we're in right now, we're worried about COVID-19 or coronavirus. And if you think about how transmission has to take place, for all practical purposes, people have to get close enough together for the disease to transmit. This is what we talk about when we're trying to limit the rate of exposure by social distancing. Okay, and that's in fact why we're doing this online, because although you can transmit viruses online, right, it's not this kind of virus. Now here's the other thing. In order for new bonds to form, the molecules have to collide in such a way that the atoms can make the bonds that are in the product of the reaction. So for example, I have this one of two NOs, right? I have NO, like this. And it turns out in this reaction, in order for, and we think about Lewis structure, right? NO will have something like this. And that's not the complete Lewis structure. This is kind of a complicated one to draw because there's an odd number of electrons in it. But in order for it to form NO2, NO2 looks like this, NO and O, right? So you'll, on the NO, it's going to have to collide with O2. And O2 looks like this. So where does the O have to strike the NO to form the product? Well, if it strikes on this side, then the new bond that forms will be between the oxygens, not the nitrogens. It turns out that that reaction doesn't proceed very far towards the product. On the other hand, if it strikes on this side, like this, then this bond can be formed. So in collision theories, we know that they have to collide. They have to be properly oriented during the collision. And then the last one is there has to be enough energy for the new bond to form and the old bond to be broken. In fact, all the energy really is for breaking the old bond that needs to be gotten rid of in order to make the new bond. So the collision has to be effective, has to have colliding molecules, has to be properly oriented, and has to have the right activation energy. So the activation energy we think of in terms of products and reactants. So let me get a pen here. I'm going to draw this graph, if I can do it. This is energy on this axis. This is time on this axis. It's called the reaction coordinate. Sorry it's so sloppy, but I'm trying to stay in the camera and not wiggle the screen too much in limited capacity here. I don't have an extra camera or anything. So if we think about the reactants having an energy and the products having energy, so this time is actually just time during the reaction. We think about if the products are lower in energy, that is going like this is exothermic. Okay, and this is my reactants, and this is my products. On the other hand, it can go like this and give me my products up here, and this would be what we call an endothermic reaction. That is, it absorbs heat energy in order to form the products. Now, regardless of which way you go, it turns out there's a barrier in energy between the reactants and the products. So if the reactants are high in energy and the products are low in energy, like when you think about a ball on top of the hill being able to roll down the hill, that's kind of this analogy here. I have a ball here and he wants to be down here. He wants to be rolling down and moving down in this direction over here. Well, you think to yourself, well, that's spontaneous. I mean, that ball should be able to roll down the hill, but what you don't think about in this analogy is somebody's got to push the ball to get it started. And the pushing of the ball constitutes an activation energy, and that energy is this, okay? And so the bigger that hill is, the higher the activation energy, the slower the reaction will go. Okay, so what does this have to do with the current challenge that we have, right, with the COVID virus or the COVID-19 virus? It goes something like this. You have a population, what we're going to be talking about here is we're going to talk about rate. And the rate of infection or infected individuals is going to be the change in N over the change in time. So we're looking at how fast people are getting infected. It turns out that you can relate that to a rate constant. Now, chemistry, we use K. In biology, I'm sure they have another symbol. But in chemistry, we'll use K as the rate constant. That's what I was talking about up here when I was pointing out that we have a little k for chemical kinetics. Right? So now, what is involved in how quickly a disease gets transmitted? And I think you can probably think about some of this yourself, right? Like, what are we social distancing? Why is that important? Why is it important that we have groups, no groups larger than 50, or maybe no groups larger than 250? Because it depends on the number of people. The rate of transmission will depend on the number of people that are in contact with each other. So that number, we'll call it N. Oops, sorry, wrong pen. We're going to call that number N. So think about it like this. If I have more people, then I'll get more people getting infected. That's the delta N over delta T. Delta means change, and change, delta N means change in the number of people, so the infected people, and delta T means over whatever unit at a time that we're looking at, okay? So, here we go. The other thing it depends on is K. K for us is the rate constant. In a general sense, when we're talking about like disease, that's the rate or the efficacy, how easily something gets infected. So if you have a high K, that means the reaction will go fast. People will get infected at a high rate, but you can also change that by having a high N. Okay? Now, there's some math associated with this, but it turns out that when we're talking about these infections, we can look at the rate, we can look at the number of people that are infected and relate it to the time in which the infections are taking place. So what I did is I pulled some data, and the data that I pulled ultimately comes from, let me slide this down here, ultimately comes from California's Department of Health. It was summarized by a news station in San Diego who is doing a COVID-19 case tracker, basically. And this is what the graph looks like from, I think it's late February to just yesterday, the 16th. And so you can see that this rate of infections is pretty consistent. It turns out in chemical kinetics, what you can do is you can go ahead and take the log of the number of cases reported and graph that against the date, right, or the number of days since the initial reported infection data. So that again, I can't remember the exact dates, but you can see the tick marks down there to figure it out. Oh yes, March 2nd, it's on the left over there. And you'll notice that when you do that, it creates a straight line. And what's interesting about this kind of data, it allows you to make predictions about what's going to be happening, presuming we don't do any social distancing, presuming that there's a uniform mixing, like people are just getting around and meeting each other, okay? And so if that's the case, we have data now. For now, we have 392 people infected. And you can see that the line is relatively straight. So what is it going to look like after 15 more days? Because this is a total of 15 days worth of data. Well, it turns out if you take this line, let me do this real quick. I'm going to just copy that, try to paste that into the presentation. I don't know if it'll let me, but I'll just try it. I have to get the keyboard up to do this, I think, so hang on a second. I don't see it. Let me try it one more time. Keyboard, click on the screen and do Control V. Oh yeah, there it is. I'll shrink it down so it doesn't take over the whole screen. But really, if you want me to post this data for you, that's fine too. I don't care where it goes. I'll do it on the next slide. There you go. So there we have, and you can tell this, I'm not going to edit this lecture. This is a live lecture. So there's our COVID cases. And so what I was going to show you is that this line is a straight line that goes like this. And this is actually the slope and the intercept. And if you've had any math, there's an r squared value. That's the correlation coefficient. It's actually 0.992, I believe. I may have typed some numbers in because I did this last night at home and it came out 995. But in any case, it's a pretty strong correlation. Assuming that we don't change what we're doing in the next 15 days, how many people would you predict? Well, you can actually use this equation and plug in 30 for x. And that gives you the log of the number of people, because this is how we generated this information, natural log. Turns out that's 4,500 people. So that's after 15 more days, if nothing changes, there'll be 4,500 infected people in California. If you look at what happens in another 15 days, so we're 45 days out from March 2nd. So that's somewhere down in the middle of April. The numbers gets to 45,000 people, and it grows exponentially like that because of the way infections work. The rate of infection isn't changing. It's just that the number of people infected is continuously increasing, and those people are continuously infecting other people. Hopefully what happens in the next near future is we limit the exposure of individuals to each other, and that could potentially just stop the virus before it really gets a strong foothold. Because right now it does not have a strong foothold in California. It's just that people keep going out and running into each other. Not because they are doing it intentionally, it's just because they don't know they're sick. Okay? So anyways, that's kind of why we're here at this point. And so maybe what we'll do is we'll continue on with our lecture, and then sort of you can think about that in the near future as we start thinking about how this is impacting our lives. So I went ahead and turned the camera off, and while you guys don't see this, I just had this long meeting that just went on. It's been a couple hours since I lectured, so hopefully there's not too much discontinuity in this, but all this stuff in preparation for what's coming up for the next few weeks, hopefully only, but possibly for the rest of the semester, but we'll get it all worked out. So anyways, we're talking about rate laws, so we'll back up for a second, because I know I'm experiencing a little discontinuity here. So collision theory, right? Molecules must collide, they have to be properly oriented, and then they have to have enough energy to react, and we call that the activation energy. This value that's here, let me go ahead and mark this out. This is the activation energy. And the bigger that value is, the slower the reaction will go. The other thing that affects the rate of the reaction is changing concentration. And I think since we're on this topic of spreading of disease and viruses and things like that, one of the things that I should point out is this makes a lot of sense, that changing the concentration of the reaction can really have a big effect on the rate of a reaction. And for example, if you have a high population density, and this is really, remember, concentration, we may have done percent concentrations already, but when we're talking about concentration, we're talking about the number of moles or molecules per liter. This is a unit known as molarity, which we'll cover actually in like chapter 12 or 13. So if the concentration changes, then the rate of reaction will also change. Now think about this. If it was the number of people in the room and you're talking about the spreading of disease, you could see why having more people in the room would increase the rate at which the disease is spread. It's the same thing is true for chemical reactions when they happen. When a chemical reaction happens, what needs to happen is molecules need to collide, and the closer together they are, the more collisions there are. So we talk about collision frequency. The collision frequency will increase, and so because of those increased interactions, the rate of reaction will also change. Now temperature, we don't have a good analogy for this one for what we've been talking about, but it turns out temperature is, well actually maybe we do. The temperature is also going to influence the amount, the rate of the chemical reaction. So think about it like this. You have an individual here, a molecule, and they want to react with this molecule over here. So let's say they travel slowly. So the rate, I'm going to go like this. They're traveling slowly, wandering around, and then they're going to collide, right? So, but what happens if they travel quickly? Like they go in a completely straight line like this, right? Then what happens is they can collide more frequently, and that's one thing. And the other thing that happens is when they collide, they'll have more energy and more probability then of creating a successful reaction. You can relate that to the sociability of individuals in a room. If they're more social and get around and meet more people, then the chances of a chemical reaction taking place or an interaction taking place that's successful will be higher. So in that context, transmission of disease is very much the same way. The amount of movement within the population also increases the transmission rate. Anyways, not to confuse this too much, but basically, changing concentrations, more collisions, more reactions, the rate of the reaction goes up. Higher temperature, more interactions with higher energy to overcome the activation energy, more reactions take place and the rate of the reaction goes up. So those are the two things that they usually talk about for changing a reaction. So let's get on to equilibrium. And your book actually has kind of a funny example. But let's think about it like this. Let's say there's a dividing line in a continent, and there's people over on this side of the dividing line like this, and then there's no one over here. So let's say there's 50,000 people on this side and then over here there's 0 people. So I have 0 people and 50,000. What ends up happening, and this is sort of the nature of people, is they tend to move around depending on weather conditions and climate, things like this. But eventually what could happen is they could jump this divide. Maybe it's a mountain range, maybe it's an ocean. And then what you'll do is you'll have more people on this side. How many people can go from the right to the left? That is, how many people can go this way right now? And the answer is, hopefully you see this is 0 because there's nobody there to move. But you have to accept the idea that once you get some people on the right side of this divide, so this is a divide, somehow divides, that's nice, divide between people, like I said, a mountain range or an ocean, things like that. Once some people get over that, then some of them may want to come back. That is, people will travel to another country and end up in that country and decide, nah, I think I need to go back. This is actually what happened with my family. My grandfather came with his 2 eldest sons in about 1900. I think it's the late 1800s, so this is a long time ago. So my grandfather came over with his dad. His dad left his 2 children in the United States. Now, how many of those, the 3, could have gone back before they were in the United States? Well, none, because there were none of them in the United States. But eventually, my grandfather needed to go back to Japan, and he just left his 2 eldest sons in the United States to grow up. And I think he came back a couple of times and visited, but I think we had some friends of family. We didn't have any family here in the United States. He came over from Japan, like I said, in around the 1890s, early 1900s. Stayed for a little while, left his 2 eldest sons, and then went back to Japan. But again, that represents something we call an equilibrium. equilibrium of sorts. That is, there's a reaction going both in one direction and the other direction. And you have to remember, it wasn't just my family doing this. There were many, many families in the United States that came through immigration. So people are traveling from one side of the Pacific or the Atlantic Ocean, coming to the United States, and then many of them ended up going back home. Not all of them. For the most part, there were more people that stayed than went back. And so what we tend to do is that situation reaches what's called an equilibrium. So equilibrium is this. Equilibrium is when the forward rate equals the reverse rate. Let me explain that to you. So we think about a reaction like this. I have A and it's going to go to B. And then B is going to get converted to A, like that. So we would say the equilibrium is equal to is when the concentration of B divided by the concentration of A is constant. And this value is known as the equilibrium constant. So that means there's a rate at which things are, like we're talking about rates of reactions. There's a rate going in this direction, right? And then there's a rate going in this direction. When those two rates balance out, it's said to be in a situation of dynamic equilibrium. So if 10 more people came, a proportional number of people would go back. Okay. Now, for the situation in my particular family, right, this would be one person back in Japan and 2 people in the United States. If we were to convert that into an equilibrium constant, the K for that would be 2/1, or just 2. You'll notice that K, this is the unit of people, right, and this is the unit of people. So equilibrium constants often don't have units associated with them, and typically we just leave the units off. So in general, when K is greater than 1, right, there's more product. Than reactant. When K is less than 1, then is more reactant than product. It's the opposite, right? So fewer people stayed, more people went back. That's essentially what we're talking about. All right, so that sort of describes equilibrium constants numerically. The unit that we use in chemistry is molarity. And it's in units of moles per liter. And when I use these brackets like this, this says the molarity of B. That's what that says to me. Okay, so we'll come back to that. I don't expect you to do a lot with that unit, but we will do some calculations which involve the molarities. So the next thing to talk about is a concept called Le Chatelier's principle. Now, in Le Chatelier's principle, excuse me, what Le Chatelier described was how a system, once it's reached equilibrium, responds to changes in concentrations, or what we call stresses, or perhaps challenges to the equilibrium. So Le Chatelier's principle is pretty much defined like this. A system at equilibrium. So we're talking about a chemical reaction that's taken place, products have formed, reactants are starting to form now. And that has reached that position where the forward rate and the reverse rate are the same. So we're at equilibrium. Okay. Responds to a change in concentration or pressure. Okay. So responds to a change in concentration, that's for aqueous reactions, or pressure to minimize that change. So for example, let's say we have this reaction of 2A plus B goes to 2C. Okay, that's my reaction. And let's say it's at equilibrium. So what does that mean about the system? At equilibrium, the concentrations, that's what those brackets mean, of reactants and products are constant. It's not that the reaction has stopped, it's just that the process is such that products are being formed at a certain rate, reactants are being formed at a certain rate, and they balance each other out. Okay, so we have it at equilibrium. Then we do this, we add some A. So what does that do? Well, since I increase the concentration of A, okay, so that's the change in concentration, what the reaction wants to do is reduce the concentration of A. So this is Le Chatelier's principle. It will do that by forming more product. That is, the reaction will shift to the right. Okay? So what does that mean in terms of this reaction? Well, it actually means the concentration of C will increase. Now, B is used, but it doesn't change its concentration. And this is a difficult concept to get across. So B will definitely get used, but because it's a solid and the concentration of the solid is really its density, it's grams per centimeter cube, its density doesn't change as it gets used up. So if you add A, then what happens is B will get used, but its concentration remains constant, and then C's concentrations will increase. What if I take A out? So we remove A. Well, since I took A out of the system, then what happens is the reaction will go this way. Because what happens when you take A out, the reaction wants to resupply A, so C goes down, and B is produced. So even though it's the reactant, if you remove some A, the reaction will try to get back to equilibrium, and it'll end up producing some of B. Its concentration doesn't change because the density of the solid won't change. But yeah, it'll get produced during the reaction. So another instance, right? Let's say I remove some C. And I'll give you an analogy for this, which usually helps people understand how these things happen. If I remove C, so I'm circling, I don't know if you notice, I'm circling the thing I'm changing. And now once I make that change, the system's no longer at equilibrium. So the reaction will want to make some more C, so it'll go that way. And I'm going to stop writing the things underneath B, but you can, I think you'll get the idea when I'll just go back and point it out. Then we're going to be removing A. So A will decrease. Okay. What if I add C? I increase C, then the reaction wants to go this way, right? And then A, well, that's what's wrong, right? A increases. So there's a physical representation of this that makes a lot of sense. And I'm going to do it like this. So I have these two tanks separated by a tube, like that. And I'm going to put water in this side. What do you expect to happen? Well, in response to the adding of the water, right, gravity wants to push the water towards the right like that. So here's what happens. Eventually, the water levels change so that the levels in the left and the right are the same. This is a system at equilibrium. So the blue now represents my equilibrium value. So now let's do this in red. Let's say I add some A. Right? I'm adding. So this is the adding right here. What happens? Well, the water is going to flow in that direction. And the volume that's here will go up until a new equilibrium is reached. And this is essentially what the Chatelier's principle is saying. A system, right, at equilibrium responds to a change in concentration or pressure to minimize that change. And then here's the last important part, re-establish equilibrium. So for this system that I drew down here with the water, that's this guy here, right? This represents the change and the challenge to the system. The system then produces more product until the levels of the two sides are the same. Right? It reaches a new equilibrium point. You could do exact same discussions with pressures. So if this is a reaction with gases. If I increase the pressure of NH3, right? So I increase this. So I'm going to go. Let me do it like this. Increase NH3. Again, that's what I'm changing. Then which way do you think the reaction will go? And then I'm going to do another one where I decrease NH2 or H2. So decrease H2. So this is what I want you to do. For each one, I want you to tell me what happens here. Which way is the arrow going to point? And then I want you to tell me what happens to all the things that are missing. So it's this, and then these guys up here, okay? Whether or not they go up or they go down. So that's all I want you to do, okay? So I'm going to pause the video. I want you to go through and do those predictions, then come back and see if your predictions matched what I wrote. Okay, so here's the answer and also a box. This was the green box. Okay, we're going to predict that one together, but that's the most difficult one to see. Okay, so now when I increased NH3, that's here, then I expected the reaction to try to remove some of that, and as a result, by going to the right, the N2 concentration went up and the H2 concentration went up to reestablish, or pressures went up to reestablish equilibrium. Now, what happens when I decrease the H2? Well, it turns out the arrow is exactly the same. This goes to the right because it's trying to make up for the H2 that was removed, okay, to establish equilibrium. As a result of the arrow being to the right, this will go down. So NH3 will go down over time if you remove the H2 in the product, because the system is trying to replace the H2 and it can only get it by removing the NH3 in the reaction. So what about the green box? And this is the one that's really hard to sort of understand for most students. And the answer is, if this arrow is going to the right, then this must also be going up. And as a result, you're decreasing the amount of H2, you're making the reaction want to go to the right, And as a result, NH3 goes down and N2 goes up. All right, so hopefully that was kind of clear to you. You can always go back and watch the video a couple times to make sure like you're understanding what's going on. These questions for these are generally all conceptual, and you just have to think your way through this process. First thing is what changed. Second thing is which way does the reaction need to go, and then the third thing is all these other boxes, what happens to those as a result of 2, that is which way the reaction is going. So continuing with Le Chatelier's principle, there's some things that we talk about in Le Chatelier's principle that are more difficult to understand without more background information. But what I want you to do is sort of learn this sort of by looking at the pattern and understanding how things work based on patterns, maybe not necessarily completely understanding how the whole process works. And one of those effects is temperature. So when we say a reaction is exothermic, let me write that in blue, exothermic. What we're saying is that the reaction produces heat or releases heat. Heat is just another word, if you remember the MCAT equation, and heat is just another word for energy. So when we write energy as a product, then energy would be on the right-hand side, right? So that would mean it's being produced, which means it's an exothermic reaction. Endothermic reactions means absorbs, endo, or internalizes, or inside, absorbs energy. That's this here, the reactant, right? So if energy is coming in as a reactant, we would say that's how we would write endothermic in terms of a reaction, as a reactant. So it's interesting to note then, if you have a system at equilibrium, this is applying to Le Chatelier's principle, and you remove the energy, what does that mean, right? How do you remove energy? Think about that for a second. Hopefully some of you got to the idea that when you remove energy, you're just lowering the temperature. So you're removing energy by lowering the temperature. So this is the thing that's changing. If you're removing the energy, which way does the reaction want to go? It means that the reaction for equilibrium will shift in that direction. So A will go up and A will go down. That's bad. A will go down and B will go up. There we go. Now, if energy is a reactant, so we remove E, that means we lower the temperature. Now, remember, the reactants and products are under the same conditions, right? So if the reaction is endothermic and we remove energy, that means the reaction shifts in this direction. The result is A goes up and B goes down. Again, the process is the same as we did before. We did 1, what happens? Right, I'll do that in red just as a highlight. 1, what happened? 2, which way does the reaction go? And then 3, predict what everything else is going to do based on that change. All right, the last thing to talk about is volume. And I will tell you how to predict, and then I'll show you how that looks in a reaction. Okay? But changing the volume during the course of a reaction can also affect equilibrium. So for this particular reaction, I have the decomposition of ammonia. Decomposition, I'm starting with one reactant and ending up with many product molecules. Right? So if I increase the pressures, this is how they'll say it, okay? or actually, I'll tell you how they'll say it in a question. If I increase the volume, the reaction goes to the side with more moles of gas. So the reaction shifts to the side with more moles of gas. And so I'm going to write that red because that's actually really the most important thing of that whole sentence, really. So for example, this reaction has 2 moles, and then this combined is 4 moles. Okay, so if I increase the volume of the reaction, it should shift to the right. So increasing volume, so there's nowhere to write that on here, right? So I'm going to say increasing volume, I'm going to go this way because there's more moles. Okay, so then what happens is, I don't have to circle that one, there's more moles going to the right, so that means N2 will go up, H2 will go up, and NH3 will go down. On the other hand, so this is increasing volume. The opposite is consistent with what we just wrote. If I decrease the volume, then what happens is it shifts to the side with fewer moles. So I'll abbreviate that, shifts to fewer moles. Okay, so that means it'll shift in this direction. This is decreasing volume. That means this NH3 will go up, N2 will go down, and H2 will also go down. Okay, so one of the things you'll need to be able to do is calculate an equilibrium constant. So I'd like to show you how you write an equilibrium constant first. And what you have to pay attention to is whether or not things are products or reactants. So here's my products, here's my reactants. And you have to pay attention to the coefficients that are in the front of the balanced chemical equation. And you have to make sure the states essentially are all the same. Now you notice this is a gas. Gases can also be calculating using equilibrium molarities. And so what I'm going to do is write this. I'm going to say K, this is the equilibrium constant. That's actually equal to what we write as products over reactants, and we use coefficients at the top. So I'm going to just randomly call X and Y. Those are just numbers. I could have used N and M as well. And the equilibrium constant, the expression itself will look like this. Is the concentration of CH3OH. And there's a coefficient of 1 here. So now the 1 doesn't affect anything, but I just want to make sure you understand that it was there. And then it's going to be over reactant, so I'm going to go CO. And that is also to the first, but here's the first one that matters, is H2 squared. Okay? Now here's the thing, when we do the calculation, don't get too hung up on like what it means exactly. Just go ahead and write the equilibrium constant and then put the numbers in and finish the calculation. So we're going to go like this. The concentration of CH3OH is this, 0.0274. We leave the units out, and there's a long technical explanation as to why, but we're not going to go into it. As long as it's molarity units, it's fine. So CO, the concentration is CO, that's what I'm going to do here, that's 0.105. And then the concentration of H2 is 0.114. And I'm going to square that number. And then I go ahead and I'll plug it into my calculator and I'll get a number. This is what I'd like you to do, is pause the video at this point, do the calculation, and then make sure you get the right number, okay? So I ended up in my calculation of 20.1, and so hopefully you were also able to get that result. Now, what if the concentrations are different, right? It says, what if the concentrations of CO are 0.250 and CH3OH are 0.058? It says calculate the concentration of hydrogen gas. So in this particular problem, we're going to assume that the equilibrium constants, because it doesn't change for the reaction, regardless of what concentrations you have, that should always be equal to 20.1. Now I want to show you something, and this is something I wish somebody had showed me much earlier about doing these kinds of problems. You don't have to write the chemical formulas all the time, and it makes the manipulation of the equation a lot easier. So for example, I'm going to call this, I'm going to change the color so you can see this. I'll do it purple. Since you're watching this at home, you can see the colors probably. That's A, that's B, and that's C. So I can rewrite this equilibrium constant as K is equal to, now I'm going to leave the brackets off. I'm going to say it's C divided by A times B squared. Now the question says that you are given the concentrations of CO and CH3OH, and it's asking you to calculate the concentration of the hydrogen gas. So that hydrogen gas concentration is this, or it's B. So I'm going to solve for B. So when I do that, I'm going to be bringing the B over to one side. Oops, I didn't mean to do it like that. I have to do it like this. I'll bring the B over to this side and the A over to this side. So basically I'm going to get rid of the denominator, and then I'm going to divide through by the things that I want to get rid of. So I'm going to pause the video. I want you to work on this for a few minutes if you struggle with this, to try to get the correct equation to do the calculation with for solving for the concentration of B. So hopefully you all got down to the correct answer. The correct answer is down here, solving for the concentration of hydrogen gas. If you didn't get there, I wrote out the steps. Normally, you know, in class I would work this out with you. You could always attend an office hour and get that information as well. But I wrote the steps out. The first step that I did was I went ahead and got rid of the denominator. The second thing I did is I divided through by K and A on both sides and was able to get B by itself. And then because I want B, not the square of B, I went ahead and I took the square root of both sides. That's why I have the radicals on both sides, and that gave me B. So now all that's left to do is populate the variables that I've created with the concentrations that were given. This is going to be actually the trickiest part because of the substitutions of A, B, and C. But what you should do in your reaction, like I did, is at A, B, and C at the very, very top up here. Right, you have to do this in order to write that equation. A is the concentration of CO, and then C is the concentration of CH3OH, which is methanol. I just noticed there's a funny bracket over here. That doesn't actually mean anything. It's just a typo. It should be a bracket. Now, I'm going to plug those values in. I'm going to say B is equal to the square root, a big radical here. Maybe get rid of, maybe make it bigger, actually. I'm going to write a lot of stuff in here. C is going to be 0.058 divided by K, which was 20.1, and A, which was 0.250. And I'll plug that into my calculator and get an answer. And I'm going to pause the video again, and I expect you to go to try to calculate it and then check your answer. If you don't get it, you know, you can always message me, but you should learn how to use that calculator to see, make sure you get the right result, okay? So that's the answer that I got. It turned out to be 0.11 molar will be the units, molarity units. And I rounded it to two significant figures because the value 0.058 only had two significant figures. Now, if you didn't get that exact answer, you should go back and make sure that you use the unrounded value for that number. That number, when you calculate it, should be this value here, 20.079. Since I reported the number up here, I did it as 3 sig figs, but the number I'm using in the calculations is actually the unrounded number that I stored in the calculator. All right, so last thing to talk about is activation energy, catalyst, and equilibrium, and how those two things affect the equilibrium. So we talked about rates of reactions, and activation energy is associated with the rate of a reaction. What a catalyst does is it lowers the activation energy. By lowering the activation energy, it allows the reaction to run faster without increasing the temperature. Remember, the things that can affect the rate of the reaction are changing concentration, addition of and changing temperature. But if you don't want to change the temperature, what you have to do is you have to lower the activation energy. And what a catalyst does is it makes it easier for the reactants to become products, okay? How does it do this? A number of different ways, but in essence, it makes sure that when the molecules collide, generally speaking, they have the best orientation for the reaction to take place. So we talked about collisions and then the orientation during the collision. It's the collision orientation the catalyst usually affects. A catalyst in biology is what we know as an enzyme. Enzymes, all they do to make reactions go faster is they take two components of the reaction that maybe don't come together optimally very easily and force them to come together in the right orientation. Okay, it's kind of like the matchmaker of molecules. It makes sure the two components come together at just the right time. Now, equilibrium is not affected by a catalyst. Equilibrium is how much product you have to how much reactant you have. It turns out when you have a catalyst, not only does it make the reaction in the forward direction go faster, it also makes the reaction in the reverse direction go faster as well, because the barrier to energy going forwards and backwards is the same. So catalysts lower the activation energy, make the reaction go faster, but don't affect the equilibrium. And that's it for this week's lecture. Hopefully, if you have questions, I will be holding regular online office hours. Feel free to contact me or text me, and if you want to meet on Zoom, because I'm being told not to actually meet with students, meet on Zoom, then I can meet with you and give you some additional help and maybe clarify different points in the lecture.